Hello students, we will talk on monotone sequences. To see monotone sequences, we need it's like a function that when we say that the function is increasing or decreasing, same way here the concept of monotone sequence is there. For being a sequence monotone and bounded, two concepts when come together, then we can find a condition for the convergent sequence. So first of all, we will define a monotone sequence. So we know that Sn is a sequence and the sequence is said to be increasing if the terms of the sequence from S1, S2, S3 goes on increasing. Now here we are using two words to generalize it, non-decreasing and non-increasing, because if you say increasing, then it is strictly less than. If you say decreasing, then it is strictly greater than. So we will use these words. Let us write down the definition. First, monotone increasing sequence. A sequence Sn is said to be non-decreasing. So you can say this is increasing, non-decreasing if S1 is less than or equal to S2 is less than or equal to S3. For all the terms here, it satisfies it for all the terms. For all n belongs to I. Same way we can define monotone decreasing sequence. So just here the change, S1 is greater than or equal to S2 is greater than or equal to S3 and so on. And here you will get non-increasing and here decreasing. A sequence Sn is said to be non-increasing. So we can use this while saying non-increasing means decreasing sequence. If S1 is greater than or equal to S2 is greater than or equal to S3, greater than or equal to Sn, Sn plus 1 for all n belongs to I. So for example, the sequence here, if you consider example, this is the sequence 1 upon n. So very simple example. This sequence is non-increasing Because the highest term of this sequence is 1. If we start to write down the terms of this sequence, then we will get the terms like this. So 1 is the highest term, and then all the terms gradually decreases. So we can say that this sequence is non-increasing sequence. Another example, one of very simple example, this sequence, we know that this is, or suppose here I will add this number. Then again, this is increasing sequence. So this sequence is, we can say, non-decreasing, means increasing. Now, if I consider this example, then this sequence is neither increasing nor decreasing, because it has only two terms, either 1 or minus 1. So these are some examples. Now we have the concept of a bounded sequence. We have seen that a sequence is bounded because we want to combine now these two results, monotone sequence and bounded sequence, and to find out the condition to check, how to check that the sequence is convergent. So this is very important criteria for a sequence, and only one method to check whether the sequence is convergent or divergent. Using epsilon and definition, that is basic definition. Okay, that is, you find a limit and confirm that whether that limit exists by epsilon and definition. So that is the definition. But this is a criteria to check whether the given sequence is convergent or divergent. So for this, we need this both. We have to check it whether it is monotone, that is either non-decreasing or non-increasing. And then secondly, as per that nature, whether it is increasing or decreasing, as per that nature, we have to check that whether it is bounded below or bounded above. Because some terms are, some things are, characteristics are obvious that we will see. So now we have seen the bounded sequence, that a sequence is bounded if there exists m greater than 0 such that modulus n is less than or equal to m for all n belongs to I. Okay. So this result, and which is bounded above is convergent. Proof of this: consider the sequence, consider the sequence Sn of real numbers what is given to you. The sequence is non-decreasing as well as it is bounded above, means it is bounded, right? So what is given? Let us write down. Given sequence Sn is non-decreasing and also bounded above. So first we will use this, that it is non-decreasing. So as the sequence is non-decreasing here, therefore the set, so we will say, consider the set of all the terms of these sequences is non-empty subset of R and which is bounded above. Which is bounded above. Given that the sequence is non-decreasing, so therefore this set is non-empty subset of R. So obviously there exist some terms, and also as per the criteria here in the theorem hypothesis, you have given that it is bounded above. What we want to prove? To prove that the sequence Sn is convergent. Okay. So to prove that the sequence Sn is convergent means to prove that limit of the sequence exists. That is, for given epsilon greater than 0, we have to find such n such that modulus of Sn minus L is less than epsilon for all n greater than or equal to n. So this we have to find. It is not sufficient to check only convergence. How to check the convergence? Convergence means its previous step is whether the limit exists. And the limit exists when? If it satisfies that criteria, that modulus of Sn minus L is less than epsilon for all n greater than or equal to capital N. That we want to show. Okay. So now here, as this sequence is bounded above, it has least upper bound. So suppose it is M. So since the sequence is bounded above, it has the set, we can say that this set, okay, this set has LUB, list upper bound, say capital N. Therefore, Sn is less than or equal to this capital M for all n belonging as this set has this list upper bound. Now let me consider one number here. Suppose these are the numbers of sequence. Here it has its list upper bound, right? So all the terms here of the sequence is less than or equal to this number. Now I will consider one number m minus epsilon here. So obviously m minus epsilon is less than capital M. But there may exist some terms of the sequence which lies between these two numbers. So only this terms satisfies this relation that m minus epsilon is less than this terms is less than capital M. So suppose the first term is Sn, capital Sn, that I will here consider. So all the terms Sn, then Sn plus 1, Sn plus 2 lies between this m minus epsilon to m. So let us write down that. The number m minus epsilon is not LUB, is not LUB of the sequence Sn. And from the diagram now, better way you draw this diagram so you will come to know that which terms we are considering. So there must exist some terms between these two numbers m minus epsilon and m. So therefore, for some capital N, we have m minus epsilon is less than or equal to Sn is less than capital M for some particular N. So now here I will generalize this result as m minus epsilon is less than or equal to Sn, and this is the first term. So Sn is less than or equal to this terms of Sn, because there are some terms between these two numbers and which is less than m. So I want to say here that there exist some terms of the sequence here which lies between these two numbers. So if I'll skip this, if I'll omit this Sn, then what I will get the result? So this implies so the proof is clear now. So this implies m minus epsilon is less than or equal to Sn, or you can say here now, because there must exist some term which is strictly less than, here Sn is less than m. Now obviously this m is less than m plus epsilon, because epsilon is some positive number. Here you can say for some n we have the number m minus epsilon is not MUP. Epsilon is small positive number. Here you can mention this. And that we are choosing for all n greater than or equal to n. So if you say this, what we are getting, m minus epsilon is less than Sn is less than m plus epsilon for all n greater than or equal to m. So therefore, modulus of Sn minus m is less than or equal to epsilon for all n greater than or equal to n. So here the interesting thing is that the sequence is not only convergent, but it converges to m. That is the upper bound of that sequence. So very interesting thing and very useful term. So this implies limit of Sn as n tends to infinity is equals to m. If we have assumed that it is least upper bound of the sequence. So if you have monotone increasing sequence, that is non-decreasing sequence, and if the sequence is bounded above, obviously as it is non-decreasing sequence, it is bounded below. Means we can say that the sequence is bounded. So if the sequence is non-decreasing and bounded above, then the sequence is convergent and converges to its least upper bound. That is very important criteria and very useful to check whether the given sequence is convergent. So this implies the sequence Sn is convergent and converges to its LUB. Similarly, we can show that if the sequence is non-decreasing and bounded below, because if the sequence is non-decreasing, it is always bounded above, and if the sequence is bounded below, then it is convergent and converges to its lower bound. So this is one of very two important results. So if we combine both of this, then we can say that a monotone bounded sequence is always convergent. Combination of these two statements. So that's